Hello, everyone. Welcome to the AI Agents Hackathon live streams.
The AI Agents Hackathon is a free virtual hackathon running from April 8th to April 30th.
We're hosting over 20 live streams where you'll learn how to build agents using various Microsoft technologies. At the end of the 3 weeks, submit your project for a chance to win fantastic prizes.
And now over to our friends at Reactor.
Hi, everyone. Thanks for joining us for the AI Agent Hack. Before we start, I do have some quick housekeeping. Please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is recorded. It will be available to view on demand within 24 to 48 hours. With that, I'd love to turn it over to our speakers for today. Thanks for joining.
Hello, everybody. I'm Laurie Voss, VP of Developer Relations at LlamaIndex. In a former life, I co-founded NPM Inc. So some of you may know me from then. These days, instead of JavaScript, I'm talking about AI, although today I'm talking about AI in JavaScript. Today, I've got nearly an hour to talk to you, so we're going to be covering quite a lot. We're going to start with the basics. What is LlamaIndex? Why should you use it? Then we'll talk about agents and about RAG and why those things are important. Then we'll dive deep into actual code, showing how to build with LlamaIndex.TS, affectionately known as LITS, including how to build a full stack web app that incorporates everything that we've learned. So what is LlamaIndex? Well, it's a bunch of things. Let's start with the most obvious. We are a framework in both Python and TypeScript that helps you build generative AI applications. We're going to be talking about the TypeScript one today, obviously. We are open source and free to use, but that is not all that we do at LlamaIndex. Llama Parse is a service from LlamaIndex that will parse complicated documents in any format into a form that can be understood by an LLM. This is critical for lots of Gen AI applications, because if your LLM can't understand what it's reading, you'll get nonsense results. Llama Parse is also free to use for 10,000 pages a month, so it's easy to try out and you get a lot of free tries. Then there is Llama Cloud, which is our enterprise service. This allows you to connect your enterprise data sources, whatever they are, documents, Google Drives, databases, and have their contents automatically parsed for you by Llama Parse and indexed into a semantically searchable form. You can think of this as LlamaIndex building a best-in-class LlamaIndex application for you. Llama Cloud is GA and anybody can sign up, and it's available in an on-prem version for big companies. So why should you use LlamaIndex? Because we will help you go faster. You're at a hackathon, so you have limited time and you have actual business and technology problems to solve. So you don't want to get stuck at figuring out the basics. You'll get to skip the boilerplate, you'll avoid early pitfalls, and you'll get a bunch of best practices for free to get to production faster. What can you build in LlamaIndex? Well, anything you want to, obviously, but there are two things that we're particularly good at. One is AI agents, and the other is Retrieval-Augmented Generation. Those two really work really well together, and I'll be covering how to do both today, in addition to what both of those things are. Before we talk about the how, though, it's worth covering why you want to build these things. And before I do that, I should define what an agent is. It's a term dramatically overused in the industry to the point of being meaningless, but when I use it, what I mean is semi-autonomous software. You give it a goal and a set of tools, and it uses an LLM to decide how to achieve that goal and what to do with those tools. Those tools can do anything. They can retrieve information about the world, or they can take action. Agents are a dramatic departure from traditional programming, where you define exactly what's going to happen in what order. In an agent, LLMs are given decision-making power. They decide what tools to use, what order you use them in, what arguments to pass to those tools. They're extremely flexible and powerful. So why build an agent? Usually, when you have messy, unstructured data and you're trying to do something useful with it, LLMs are extremely good at handling messy inputs, and the world is full of messy inputs, so agents have a lot of applications. In general, I regard a good agent use case as any situation where an LLM is required to take a huge body of text or images and turn it into less text. Reading emails, handling customer service conversations, interpreting contracts, processing invoices, applying regulations, summarizing documents, these are all great use cases because you have a huge body of text and you need to turn it into something smaller: a calendar event, a decision, a report, an answer to a question. The most obvious application of LLMs is a chat interface where you give it questions and it responds with answers. But I encourage you to think beyond the chatbot model. LLMs are capable of taking unstructured data and turning it into structured data like JSON, which can then be passed to regular software, making that regular software suddenly capable of handling complex, messy data that it never could before. LLMs under the hood is a huge application surface, much bigger than the market for pure chatbots. You'll notice that I've talked a lot about what LLMs can do with unstructured data. LLMs are trained on mountains of public data, but unless you are building something extremely generic, you're going to want them to act on specific data, your data. And they don't have your data, so you have to feed the LLM your data. The problem is that you probably have tons of data. You probably have tens of millions worth of tokens, and even the best LLMs can only take about 1 million tokens at a time. Even if you have less than 1 million tokens of data, LLMs charge you by the token. So giving them all of your data every time you have a question is expensive. The solution is Retrieval-Augmented Generation, or RAG. The way RAG works is you take all of your data and you pass it through a technology related to LLMs called an embedding model. This converts your strings of data into arrays of numbers called vectors. These vectors represent the meaning of that data. The total set of possible vectors is known as vector space. So what you're doing is known as embedding them in vector space, or embeddings for short. Then, when you get a query about your data, you pass your query through the same embedding model, and through the magic of semantic encoding, your query ends up mathematically nearby in vector space to the data most relevant to answer that question. So you retrieve that relevant data and you pass that data and your query to the LLM and it generates an answer, hence Retrieval-Augmented Generation. So agents can use RAG as one of their tools to access mountains of private real-time data that far exceeds what their training data covered. Agents need RAG, but RAG also needs agents. Agents are capable of introspection. Could this complicated question be a set of simpler questions? Did I just give a sensible answer to this question? Do I need to try extracting that data again? They can handle error correction. They can handle the unexpected in a way that RAG by itself cannot. In December of last year, Anthropic did an excellent post about how to build agents. It drew on their experience of building agents and formalized 5 core patterns that we recognize from our own agent work: chaining, routing, parallelization, orchestrator workers, and evaluator optimizers. What I'm going to be doing today is showing you how to implement those agentic patterns in LlamaIndex to achieve fully capable agents. The first and most obvious pattern is the chain. You use an LLM to do some work, and you pass the output to another LLM and so on to complete a task. For example, one LLM could parse a document, the second could summarize the parsed data, and a third could make recommendations based on the summary. LLMs do better when given a single simple task, so chaining is a great way to accomplish complex things. It's trivial to build, as we'll see later. The next pattern that Anthropic called out is routing. In this pattern, you create several LLM-based tools to solve a problem in various ways, and you give an initial LLM the choice of which tool to use. One way we might use routing is if you had several databases, each specialized to a specific domain. The first LLM call can look at the query and decide which database is most likely to have the answer, and route the query that way. Again, not that complicated a concept. The next pattern is parallelization, which is where things get a little bit more interesting. Anthropic defines this as running several LLMs in parallel and aggregating their results. They define parallelization as having two flavors. The first is sectioning. This is where you take the same input and act on it in completely different ways. An excellent example is guardrails. In one track, you ask the LLM to answer the user's question, and in a separate track, you ask the LLM to scrutinize the question to see if it's asking to jailbreak or to do something illegal. This allows you to preempt the output and cancel work before you do something dangerous. The other flavor of parallelization is voting. This is where you give the same task to different LLMs and you see if they all come up with the same answer. Then you can take a unanimous or majority vote and reduce errors and hallucinations that way. LLMs are famously non-deterministic, so getting them to vote on what the right answer is a way of reducing that level of non-determinism. The next pattern is orchestrator workers. You can use an LLM to look at a complex task like a multi-part question and split it into several simpler questions and ask each of those questions in parallel. You then collect all of the answers and get another LLM to synthesize a single response that answers the full question. We'll be building exactly this later. The final pattern that Anthropic is the one that Anthropic called the evaluator optimizer, but which we think is more commonly called self-reflection. In this pattern, you use the LLM to decide whether the LLM has done a good job, and you give it a chance to try again, optionally with feedback that might help it do better. The real power here is obviously combining all of these patterns. You can create arbitrarily complex workflows to handle any combination of circumstances. So with that understanding of the underlying patterns, let's now dive into the nuts and bolts of LlamaIndex and how we actually build these things with it. The building block of agentic programming in LlamaIndex is the workflow. It is a flexible, event-based programming model. Workflows are a series of steps connected by events. Agents can do anything at any time. That's both their power and their danger. Workflows allow you to shape the paths that your agents can take, leaving flexibility where it's useful and structure where that makes more sense. Let's look at how we build one. All of the example code I'm going to show you is available in this public repo. You'll get a link to this at the end, and I see that Pamela has already shared it in the chat. So don't sweat if you miss it, because all of this code is available later. First, let's get some basics out of the way. We're going to be using TypeScript, so we're going to use TSX to run it for us. The workflows are in a package called LlamaFlow Core. We want to use top-level await in these examples, so we're going to add type module to our package.json. We need only three things for a basic workflow: create workflow, workflow event, and pipeline to handle the output. If you're in the repo, all of this stuff is taken care of for you already. You just need to run those 2 npm installs. Workflows are event-based, so the first thing we need to do is define some events. Conventionally, we always have a start event and a stop event, but you can name these things whatever we want and then create the workflow itself with create workflow. Now we create handlers called steps. A step usually receives one kind of event. That's the first argument there. And it can emit one or more events, which will trigger the next step or steps. Here you can see our first step accepts a start event, and we emit a second event by returning it. Our second step is triggered by the emission of the previous event, and it accepts that second event and returns a stop event. That's all there is to it. You've created a chain. To run a workflow, you trigger that start event. You can use the send event method, which you can pull out of the workflow itself. We're also pulling out an event stream, which we're going to use to process the output. The with method, you'll see used all the time in workflows, attaches data to an event. You can see us pulling the start event's data out of it and doing it again in the second step if you look at this previous code. You can see the second event with start data, and you can see stop event with second data. Workflows output a stream of events. Every single thing that happens is output, which is useful for debugging what's going on and for displaying progress to the user. In this case, we simply log every event that happens when we see the stop event. We treat it specially and halt the processing of the stream. The final result is what gets logged at the end. So here in this code, you can see us processing every single event, outputting a console log for every event. And when we see a stop event, we return a result string with the event data. In a real app, obviously, we'd have LLMs doing things, and it wouldn't just be outputting random console logs. But don't worry, we're getting to that. Let's move on to our second agentic pattern, which is routing. The setup for this is the same as chaining. We've just created a different set of events. Effectively, we've created two chains, A and B. You can see them as branch A1 event, branch A2 event, branch B1 event, and branch B2 event. The core of routing is that you pick a branch. In a real app, you'd get the LLM to do that. You could ask it to output A or B. Here we're just doing that using a random math event. But the key thing here is that we are returning either a branch A1 event or a branch B1 event. And that is getting us onto one branch or the other. Our steps look very similar to our steps previously because they are both chains. Step A1 goes to A2, step B1 goes to B2, and they both emit stop events at the end. Processing them with stream handling looks exactly the same as before. We'll just get different output at random. But next, things get more interesting. We talked about two flavors of parallelization, voting and sectioning. We'll look at sectioning first. This is going to require some new constructs, collect, until, and filter. This is how we bring them in. And we'll also see how to use them. We'll see how to use them next. We'll also need the getContext method, which we can pull out of core. For our events and sectioning, I've created 3 branches. Unlike in routing, instead of picking one, we're going to run all 3 at the same time and collect the output from all 3. We create our starting step, and we use the sendEvent method to trigger all 3 branches. Notice that this is different. Previously, we triggered events by returning them, but that allows us to only return one event at a time. Now we're explicitly triggering events, and we can trigger as many as we want. So we trigger all 3 here. The steps that we're triggering here are pretty simple. They all trigger a single event, the branch complete event. Those branch complete events are what we're going to look for in the output to know that we have completed those branches. Back in our starting step, we collect those events using collect, until, and filter. What these do is they sit on the event stream and they look for branch complete events specifically until the condition is met. In this case, the condition we've decided to wait for is that we've seen 3 events. Once that's done, we can emit an all complete event. And that step can do whatever it wants with the output. Processing the output looks just like it did before, so I'm not going to repeat that code. The other kind of parallelization is voting. It's very similar, but instead of separate steps, we can trigger the same step multiple times and then take a majority vote of the output. It's so similar that although voting is in the repo, I'm not going to step through it here. Let's move on to orchestrator worker. For this example, we're actually going to use an LLM, so we need to do a little extra setup. First, we set up a .env to pull from our, we set up the .env package to pull from our .env.local file. And then we go to Anthropic and get a free API key and put that in the file. Then we install the LlamaIndex Anthropic package and import it. I'm using Anthropic here because it happens to be my favorite LLM. If you don't want to use Anthropic, LlamaIndex supports 14 other providers that you can use, including OpenAI, Azure OpenAI, DeepSeek, and even local models running on your laptop. For the orchestrator worker pattern, we're going to ask our LLM a complicated question, and we're going to tell it to split that question up into a set of simpler, easier to answer questions. Then we're going to use parallelization to answer them and bundle the answers together at the end. Once we've got at the end, we will get an LLM call to answer the full question using the data from the simple questions. This example is a little bit silly because we're getting all of the answers from the same LLM, but you could combine this with routing and RAG, for instance, to have multiple different data sets online and have the LLM pick the best one to answer each question. We need our LLM to do stuff, obviously, and so we need to initialize it. This is how you do that. It's pretty simple. Splitting up the question is mostly a matter of prompting. Here, I'm telling the LLM to split up the question and return one question on each line. And then I'm doing some very basic string splitting to get each of those questions by splitting the string up on breaklines. Note that I've had to tell it to be quiet because otherwise it tends to include a preamble explaining what it just did. Our question answering is a single step that we trigger multiple times. Here, obviously, we're just asking the same LLM, but it could be a different LLM or a database or anything. Emitting our questions and collecting the answers is exactly how we did it in sectioning and voting. We send a lot of events, we collect and filter. So you can see us calling send event multiple times. And this time, the condition that we're waiting for is that we have received the same number of questions that we sent. We then bundle them up and emit a synthesize event. In this case, we've just put all of the answers into a single block of text separated by breaklines again. We also send it the original question so that it knows what it's trying to do. This is our new final step. We take a set of answers, we give it to the LLM, and we say, make a single coherent answer out of this. Ta-da! That is the orchestrator workers pattern. Our final pattern from Anthropic is the evaluator optimizer, also called self-reflection. The core of this pattern is the ability for an LLM to look at the output of some other LLM and say, is this good or not? Does it need more work? In a later example, we're going to show how to do that in full. But here, we're just going to show you how to loop, which is extremely simple. Imagine a chain with steps A, B, and C. Here in our C step, we examine some condition, in this case a counter, and if we need to loop, we emit the start event all over again. That's it. Event-based coding is really nice that way. You could emit any of the relevant events to go back to that event. You don't always have to go back to the start. All of these agentic patterns are all well and good, but you are at a hackathon and you need to ship stuff right now. So how do you get all of this stuff into a web app? Because let's be honest, that's what you're building. We've been slowly walking our way through examples in the repo, and the next one is about a React app, specifically a Next.js application. I'm just going to assume that as a JavaScript developer, you've used React before, because statistics show that nearly everybody who writes JavaScript has used React before. And I'm using Next.js because it's similarly very popular. So let's just kick off a vanilla Next.js app and accept all the defaults and look at our React-based homepage, which is sitting at the path on the screen in the repo. What this app is doing is very simple. When the page loads, it kicks off a workflow. As events happen, they are logged to the screen, and when the workflow completes, it says so. This is all vanilla React event handling stuff on this screen. We're going to fill in those 3 dots next. You can see us with an updates and set updates pair and an is complete, set is complete pair, and we're just listing all of the updates as they're on the screen. Workflows can be built entirely in your browser. You can use this if you're working with remote LLMs or really any other control flow situation. You'll see I've created, just as before, a start event, an update event, and a complete event, and I've created the workflow. What we're doing inside of our React app is simulating server calls and sending update events when they happen. So you see a series of set timeouts here. And they're calling send event, which is, and each send event is sending an update event with a string. This is the novel part here, handling a workflow stream in a React app. As you can see, we're using in-browser stream events, and we're detecting update events as we did before. The only difference is that we're calling our setUpdates function to trigger an update in the UI whenever an event happens. The takeaway here is that workflows work in a browser. But what if you want them to work on the server instead? After all, you want to call an LLM with an API key, and you probably don't want to leak your API key to the client. So let's see how we do that. You'll find this next set of examples in the repo at 8 server. If you're building an agentic app in LlamaIndex, this is a great jumping up point because it's pretty much a fully working React app with workflows built in. Our client-side React code in a server-side situation is greatly simplified. The JSX part remains the same. We're still just outputting a list of events. But the use effect portion is now calling an API endpoint and using an event source to get streaming updates. Event sources are an excellent way to relay the progress of your workflow to the user as it happens, since workflows can take a long time to run and you don't want your user getting bored and wandering off. Now let's look at how that endpoint is created. We're going to read this code from the outside in. So first, we create a get endpoint because all event sources have to be get endpoints, and we create a readable stream. Everything inside of the method that we're going to talk about happens inside the start method of the readable stream. We pass our readable stream immediately to next response with some headers to make it work properly. An event source is an extremely simple protocol. It's just text with the word data and a colon followed by anything you want, and then 2 breaklines. That's what we're pushing out here to start. You can see data connected to workflow. That's all there is to it. It's just text. While we're at it, we've initialized our LLM just as we did before. Our app this time around is going to do something a little bit more real than our previous examples. It's going to be a blog post writer. It will do research on a topic. It will write a blog post based on that research, and then the LLM will self-reflect and decide whether that blog post is good enough or if more research is required. It's still a little silly because we're going to be using the LLM to do the research when a more realistic app would use RAG, but we're going to cover RAG later. Here, as usual, we're setting up our events. I've gone a little bit more fancy with the types this time instead of just using strings for everything. But you can see a start event with a topic, topic, research, and feedback properties, a write event, a review event, and a stop event. A feature we're going to use here for the first time is the context store. This allows us to create persistent memory between steps without having to pass it all in the events. We add the store to the workflow when we initialize it, and we set the original state at that time. In our starting step, we're doing one of 2 things. Either it's our first time around, in which case we simply prompt the LLM to research a topic and then send that research to the next step. Or if it's a loop, then there's feedback, and we attach that to the research request so it does better research this time around. You can see that in this logic here. We have a base prompt, but if feedback is populated, we attach the feedback. Then we call LLM complete with our prompt, and we return a write event with the results of that prompt. Writing the post is simple. We take the research and we prompt the LLM to write something with it. Honestly, the tricky part here is trying to get the LLM to use only the research and not other stuff that it already knows about the topic. This is a pretty common real-world problem with RAG. You want your answers from your LLM to be based only on the context that you give it and not things that are in the LLM's training set because you don't know where those things came from. We also stash our research into the store so that we can use it later if we need to. Now here's our self-reflection. If the LLM thinks the post is good, it just returns the word good. And if it doesn't, it responds with lengthy feedback. And we loop back to our start event using our stored topic, research, and feedback. You can see the call to LLM complete and the simple if-else on what the value of the text is. We run the workflow just as we have before. The only difference is in our processing. We use the stream controller to send our event source formatted data back to the front end so that it can see everything that happens. In a real app, we might want to filter these so that we don't send every single event to the front end, just the important ones. We might even emit special events just to be captured and displayed that aren't otherwise part of the workflow. Okay, so we've learned a lot so far. You've seen all of the agentic patterns and how to implement them as workflows. You've seen how to take workflows and bring them to a browser or bring them to a full stack app. And there's two last things we have to cover: adding agents to the mix and adding RAG to our agents. But wait, adding agents, haven't we been making agents this whole time? We absolutely have been creating agentic software managed by LLMs with decisions and everything. But we said one of the key features of agents is tool use. And the simplest way to use tools in LlamaIndex is to spin up a little agent to use the tool for you. So our big agents will operate little agents in a lovely little multi-agentic system. Let's see how that works. First, we need some new imports, and we're finally going to install LlamaIndex Core. So far, we've only been using workflows and the LLM integrations. Tools in LlamaIndex can be anything. They are just regular functions. You can get them to call third-party APIs, read the file system, whatever you want. Here we have a really dumb tool. All it does is add up two numbers. LLMs can add up numbers by themselves. This is just for the example. To allow the LLM to use the tool, we have to tell it how to call it. This is the most complicated part of creating a tool for an agent. You have to give it a name and a description, and the LLM will use these to decide which tool to call and what that tool does. So it's very important that the name and description be very descriptive. Then you have to define the parameters of what each argument does. This is how the LLM knows what parameters to use. And finally, you give it the function itself so it knows which function it's supposed to be calling. You pass all of this stuff into the tool function that we imported earlier. You're now ready to create your tool using agent. Agents all use LLMs under the hood, so we use settings.llm to tell it which one to use. In this case, we're again using Anthropic. You then call your agent and pass it an array of tools. In this case, the array just has one tool in it. Calling your agent from inside a workflow step means calling agent.run. The results of your agent will be in data.result, and that's it. Your workflows can now run sub-agents, which can call any tools you want. Remember, these tools can do anything. They can fetch data, they can take actions, therefore your workflow can do any of those things. One thing you're really going to want to do is give your agents data using RAG. So to wrap up this tutorial, let's see how that's done. Let's talk about how you build a RAG pipeline in practice. First, an overview. You ingest your data from wherever it lives, you parse it into smaller chunks, you run those chunks through an embedder, and you store them in a vector store. Then you use a query to perform semantic search on the chunks in your vector store. You take the chunks that you've retrieved and you pass them to the LLM with the query, and the LLM generates a response to the query based on the data you just gave it. Let's see how you do that in LlamaIndex. To get this done, we'll need some new sub-packages, Hugging Face and readers, and some corresponding imports. I'll explain what these do in a second. First, you need to get your data from somewhere, whether it's your file system, a database, or an API. In this case, we're using our simple directory reader, which loads files of all kinds from your file system. We have lots of other loaders available. Now would be a good time to use LlamaParse. LlamaParse is an excellent parser of complex documents like PDFs and things like that, but we'll be skipping it for now. But if you are interested in using LlamaParse, this is the link to the documentation that will get you using LlamaParse in TypeScript. The next step, like I said, is setting up an embedder. You need this so that you can take all of your data and search for just the semantically relevant bits of it. That is the core of RAG, as we learned earlier. OpenAI provides an embedding API that you can use. Anthropic doesn't have an embedding API of its own, so we're going to use a local embedding API from Hugging Face. This runs directly on your laptop. Embedding is pretty cheap to do, computationally speaking, so this isn't going to set your machine on fire or anything. In a real-world application at this point, you would want to store your embedded data into a vector store. That means that your embeddings persist, and you can use them over and over without having to re-embed them every time. For this toy app, however, we're going to use an in-memory vector store. But I've provided a link to our docs about how to use a real vector store. Here we create our in-memory vector store from the set of documents that we loaded earlier. This also takes care of chunking and embedding them, although you could customize how that happened if you wanted to. The core of RAG is obviously the retrieval part. Here we're going to create a retriever which accepts a string and goes looking in your vector store for the matching context. By default, our retrievers fetch the 2 most relevant bits of context, but I think that's a bit low. So here I'm telling it to retrieve the top 10. Now we've got an index and a retriever, we can create our tool for an agent to use that will do RAG for us. Just like when we used arbitrary functions as tools, we have to give the tool a name and a description, and the name and the description that we use here are very relevant. This is how the agent decides whether or not it should use that tool and what that tool can do. Here, the rest of the tool description, where we set the parameters and stuff like that, is taken care of it for us by the query tool function, which is attached to the index. Giving RAG to an agent is as simple as passing in 1 extra tool when instantiating your agent. So previously, our tools array was just add tool. Now it includes the query tool as well. So you have learned a lot. You can create agents using arbitrarily complex workflows. You can give them arbitrarily complex tools, and you can give them an enormous amount of power with RAG. And you know how to put them into a web app. That is a whole lot of capability. Let's talk very briefly about what RAG can't do, because it will help us contextualize why we learned all those other patterns. In real-world situations, RAG has trouble answering some kinds of questions like summarization, comparison, and multi-part questions. To address those issues, you use the techniques we discussed earlier, patterns like routing, orchestrator worker, and evaluator optimizer, were specifically designed to address those limitations. Why is summarization a problem? Because RAG is designed to select a subset of your data, but summarization requires all of your data. The pattern to use here is routing and parallelization. When you see a question about summarization, don't send it to your regular RAG pipeline. Send it to a summarizer. The summarizer will have taken your documents and summarized them in advance. Or if your documents are too large to summarize all at once, it could split your document up into chunks, summarize each chunk, and then take the summaries, the chunked summaries, and create a single summary from that. It is a good idea to do that stuff in advance, otherwise your summarizer can take a long time to run. Comparison queries tend to fail in RAG because RAG will try to retrieve chunks about the same things about the things that you're comparing all at the same time. So if you say compare A and B, it's literally going to send the string A and B to your retriever, which will try to simultaneously retrieve things that are semantically related to A and semantically related to B. It'll be much more accurate if you send it as 2 separate queries where you say, give me all of the things related to A, give me all the things related to B, and then in parallel, you synthesize those into a single comparison of the answers to both questions. And finally, multi-part questions fail because RAG is good at getting context for one question. You can solve it by using chaining or parallelization to split your question up into many simpler questions and answer them separately, as we saw earlier. So now you've got a solid grounding in LlamaIndex in TypeScript. What's next is up to you. We are excited to see what you can build with all of this. I think the examples repo with its full stack app is an especially great place to start. We welcome feedback from the open source community, and that means you. So join our Discord to ask questions of your peers. This is a great place to get help during the hackathon. And also our engineers hang out there all the time. We also have extensive documentation that I personally spend a ton of time writing, so we welcome feedback on that as well. I hope that this has been a useful introduction to LlamaIndex and all that it can do, and also to the wider world of agents and retrieval-augmented generation. You can follow this link or the QR code to get all of the slides that you saw today, plus all of the links to examples you might have missed. It's been a pleasure to speak to you, and thank you all for your time and attention. I think we have lots of time for questions, as this went much faster than I thought it would. I see a question from Pamela. How similar is the code in Python? Relatively similar. The current version of workflows that you're looking at is actually the second version of workflows that we built. The first version worked exactly like the Python. And while that was convenient for people moving from Python to TypeScript, people who are sort of native TypeScript users didn't find it very ergonomic. It wasn't JavaScripty. It didn't work the way that they expected it to. So this way of putting workflows together was designed from the ground up by our engineer, Alex, to be more sort of idiomatically JavaScripty. That's made it a little bit less like the Python, but we think it's also made it easier to use. Another question, multiple agents can do a better job, but they increase latency. When do you decide to use two specialized agents? When is it worth it? That is an excellent and tricky question. In general, I find that I set a latency budget of like, how fast can I answer this question? And then I do as much as I can in that time. One of the things that can make a big difference here is if you can modify what model you're using according to the complexity of your question. So if you have simple questions, you can send them to simple models, and you can do 2 or 3 turns with like an 8 billion model and get very fast agentic answers. Or if you use a service like Grok, which provides particularly fast inference, you can get more turns of your agent in your time budget. But generally speaking, the more turns that you get, the more LLM calls that you get, the higher the quality you're going to get out of it. So it's really just a matter of setting your time budget of how long am I willing to make the user wait, and how many LLM calls can I get away with in that time. What are the big use cases for RAG agents that aren't chatbots? I say as a chatbot author. There are a lot. We at LlamaIndex focus on 3. We call them knowledge agents, data extractors, and report generators. So a knowledge agent is the closest one to a chatbot. It is going to be answering questions about a large database of information or a large set of databases of information. But the knowledge extractor is taking complex information and turning it into structured data, which it then feeds into existing software. This is a huge class of applications. So if you can imagine a calendar application that reads your emails and decides whether or not there are events in your emails that it should be adding to your calendar, the software that adds events to your calendar is just a regular calendar API, which you can add as a tool. The LLM is reading your emails, which are these messy unstructured data, but it's just creating a JSON object that it then passes to the calendar API. you don't have to chat to your calendar application to get it to do stuff. And that's what I mean by the non-chatbot kind of application. The other big class I mentioned is the report generator. There is a whole chunk of work that knowledge workers do that is taking large bodies of data and producing a smaller amount of text, producing a report or a summary or a recommendation. LLMs are really, really good at that. If you can give them a template of like, this is what this report should look like, it can split that template up into a series of simple questions that say, okay, the template says that I should talk about where this thing is happening. Let me ask a simple question of my database of knowledge that says, where is this thing happening? The template says that I should say, how many people are going to be involved? I can ask the question about how many people are going to be involved. So it can take this complex template and split it up into lots of simple questions that LLMs are capable of answering and get you like 80, 90% of the way there towards this complex report generation that a knowledge worker can then just sort of sign off on and double check. We've found in our customers that this can save, tens of hours of work on reports that take, only tens of hours to get done in the first place. Pamela, one more question. Does LlamaIndex have built-in evaluation functionality? It does. The Python version does. The TypeScript version is lagging a little bit behind on evaluation. You can use third-party evaluators for evaluation stuff. The dirty secret of evaluation is that people don't do it as much as we think they should. A lot of evaluation is done on just vibes or just done in regular unit tests, like, does this give me a good answer? Without going through formal evaluation processes. Cool. What other questions have we got? Any more? Thank you for all those great questions, Pamela. Yes. We always need to write more tests, and we should always be doing more evaluation and not just relying on vibes. But everybody's just vibing their way through the AI revolution right now. All right. Looks like we're wrapped up. Thanks, everybody, for coming, and thanks for the great questions, Pamela.
Hi, everyone. Hope you enjoyed today's session. If you aren't registered for the AI Agents Hackathon yet, register now at aka.ms/agentshack and start hacking on the agent of your dreams.
And if you have any questions along the way, just post in our GitHub discussion forum or attend our live office hours in Discord. And of course, make sure that you keep attending the live streams to keep learning about agents.
Once your project is ready, submit it before April 30th at 11:59 p.m. PT to be eligible for our prizes. Thanks for joining.